NASA's Webb telescope keeps surprising us like no other telescope before. When the James Webb Space Telescope blasted off from French Guiana on Christmas Day 2021, astronomers anticipated it would deliver breathtaking images of distant galaxies and star-forming regions, as well as analyze the chemical makeups of exoplanet atmospheres. And NASA's flagship space telescope has not disappointed. James Webb has already captured images of galaxies so far from Earth that cosmic expansion has shifted their light well into the infrared part of the spectrum, which the telescope is built to detect. And the observatory's near-infrared spectrograph has even discovered carbon dioxide in the atmosphere of exoplanet WASP 39 and b, the first definitive detection of this gas in a planet beyond our solar system. While unveiling our universe's furthest horizons, the Webb telescope has set its sights closer to home, too. Interestingly, some of the observatory's most gorgeous images are actually ones of our very own solar system. With its gold-plated hive of mirrors and backpack of infrared equipment, such as the near-infrared camera, the James Webb Space Telescope has reintroduced us to the stunning place we call home, making us feel like we're seeing our planetary neighbors for the first time, all over again. It even offered us a poignant view of Neptune's frail rings, something that hasn't been done for 30 years. But on Thursday, scientists announced that, beyond offering us fresh eyes on the solar system, Webb's images of our cosmic neighborhood are also presenting us with new data about a planet we thought we knew quite well: Jupiter. For those who don't know, Jupiter is located at a distance of 778 million km from the Sun. That is about 5.2 times farther than Earth. The distance from it to our planet varies from 588 to 967 million kilometers. This is quite a lot, but still, by cosmic standards, it is located not far from us. Jupiter's diameter is 11 times larger than Earth's. This means that the gas giant, even at this distance, reflects a lot of sunlight. The mass of this planet is 318 times the mass of the Earth. The fifth planet from the Sun, Jupiter, is what watercolor dreams are made of. Vibrant bands of clouds ripple around its thick atmosphere, making up a world so large that more than 1,300 Earths could fit inside. Its great red spot seems to peer out from the swirling vapors like an enormous eye in the face of a striped giant. Though seemingly serene when viewed from the relative safety of our homeworld, Jupiter is a chaotic and stormy place. The gas giant planet's spots and swirls come from massive storms that whip up prevailing winds as fast as 335 miles an hour, at the equator faster than any known winds on Earth. That includes the Great Red Spot, which is a massive hurricane-like storm called an anticyclone. It's far bigger and longer lasting than any tempests that have ever raged across our planet's surface. It rotates in an ever-present oval that's more than the width of the entire Earth, although it has been shrinking for as long as humans have been observing it. Jupiter is a massive ball of gas. Its clouds are composed of ammonia and water vapor drifting in an atmosphere of hydrogen and helium. The particular cloud chemistries are likely the magic behind the planet's vibrant colors, but the exact reasons for Jupiter's painted appearance remains unknown. Below the gassy upper layers, the pressure and temperature increase so much that atoms of hydrogen eventually compress into a liquid. Pressures climb so high that the hydrogen loses its electrons and the soupy mess can host an electrical charge, just like metal. The planet's fast spin on its axis means that one Jupiter day lasts less than 10 Earth hours, and it sparks electrical currents that may drive the planet's intense and massive magnetic field, which is 16 to 54 times as powerful as Earth's. Jupiter is the second brightest planet in the night sky, after Venus, which allowed early astronomers to spot and study the massive planet hundreds of years ago. In January 1610, astronomer Galileo Galilei spotted what he thought were 4 small stars tagging along with Jupiter. These pinpricks of light are actually Jupiter's 4 largest moons, now known as the Galilean moons: Io, Europa, Ganymede, and Callisto. Many of these celestial orbs are as remarkable as Jupiter itself. The largest moon in the solar system, Ganymede is also the only moon known to have its own magnetic field. Volcanoes rage on Io's surface, earning it the title of the solar system's most volcanically active body. And scientists believe Europa sports a deep, vast ocean beneath its icy crust, making it a top candidate in the hunt for alien life. But these are not the planet's only celestial tag-alongs. Jupiter has dozens more, and there may still be more to find. In 2003 alone, astronomers identified 23 new moons. And in June of 2018, researchers discovered 12 more Jovian moons that wander in oddball paths around the giant world. Since Galileo first laid telescope-enhanced eyes on Jupiter, scientists have continued to study the curious world from both the ground and the sky. In 1979, NASA's Voyager 1 and 2 spacecraft zipped by the gas giant, taking tens of thousands of pictures as they passed by. Among the surprises from these missions, the data revealed that giant Jupiter sports thin, dusty rings. And when NASA's Juno spacecraft began orbiting Jupiter in 2016, it quickly started sending back breathtaking images. The stunning pictures revealed that the planet is even more wild than we once thought. Juno returned some of the first detailed looks at the planet's poles, which revealed cyclone swarms gyrating on its surface with roots that likely extend deep below the upper bands of clouds. Though Jupiter has been so intensely examined, many mysteries remain. One enduring question is what drives Jupiter's great red spot, and what will happen to it in the future. Then there's the question of what actually lies at Jupiter's core. Magnetic field data from the Juno spacecraft suggests that the planet's core is surprisingly large, and seems to be made of a partially dissolved solid material. Whatever that is, it's searing hot. Scientists estimate the temperature in this region could be up to 90,032 degrees Fahrenheit, hot enough to melt titanium. And as James Webb opens its eyes on the universe, Webb scientists have high hopes for what the next Webb Space Telescope can teach them about the Jovian system. Researchers plan to analyze the world's cloud layers, composition, temperature, winds, and auroral activity. Astronomers also wish to better understand the structure of Jupiter's ring system, providing insight into where it originates and how it will evolve. And finally, planetary scientists expect to create maps of the surface and atmosphere of both the volcanically active moon Io and the icy moon Ganymede. These satellite observations will also search for plumes of volcanic gases and water vapor. It's an ambitious undertaking, but James Webb has shown that it's truly worth every single penny. The premier observatory is taking us beyond what anything else has seen. Images the observatory took of the gas giant last year have managed to show us brand new things about its moons, atmosphere, and rings. Basically, after examining images the Webb telescope captured of Jupiter in 2022, a team of researchers realized there's a high-speed jet stream on the planet that's more than 3,000 miles or 4,800 kilometers wide and traveling at about 320 miles per hour or 520 miles per hour. This is something that has never been seen before. As Ricardo Huso of the University of the Basque Country in Bilbao, Spain, and lead author on a paper describing the findings, said in a statement that totally surprised us. It's amazing to me that after years of tracking Jupiter's clouds and winds from numerous observatories, we still have more to learn, Leigh Fletcher of the University of Leicester in the United Kingdom, a member of the new study, said in the statement. According to the team, this newfound jet stream on Jupiter that's blasting away at about twice the speed of a Category 5 hurricane on Earth and sits right above the equator might shed some light on the planet's turbulent atmosphere. In fact, all of those Jupiter images captured by James Webb might help researchers deduce what goes on in the skies of the apricot-striped orb. Like Huso said, what we have always seen as blurred hazes in Jupiter's atmosphere now appear as crisp features that we can track along with the planet's fast rotation. Jupiter is notorious for its extreme weather. For instance, Jupiter's great red spot we've previously mentioned, a never-ending, enormous storm that's so huge it's visible from our vantage point on Earth with a regular old optical telescope. And, importantly for science investigations, Jupiter's atmosphere is layered, like Earth's. This means wind speeds in different layers are probably contributing to the giant planet's tumultuous climate. It's also why Huso and fellow researchers hope to compare what James Webb's infrared vision has seen among Jupiter's high-altitude atmospheric layers, which reveal the new jet stream via some cloud-related features with what the Hubble Space Telescope has already seen in deeper layers. Hopefully, that'll give us a pretty clear picture of those wild Jovian winds. In fact, Hubble images, which are primarily associated with the visible and ultraviolet parts of the electromagnetic spectrum, have already helped out, offering information about what the area around Jupiter's equator usually looks like, so the team could have a baseline before studying Webb's equatorial jet stream data and regarding other storms in the region unrelated to the jet. According to Michael Wong of the University of California, Berkeley, who led the associated Hubble observations and was a member of the new study, we knew the different wavelengths of Webb and Hubble would reveal the three-dimensional structure of storm clouds, but we were also able to use the timing of the data to see how rapidly storms develop. In other words, the team explains, that comparison could help us understand how wind speeds on Jupiter change with altitude and generate what are known as wind shears, which are kind of like wind speed gradients over short distances. The extremely fast jet itself is located about 25 miles, 40 kilometers, above the planet's cloud tops, so if lower winds exhibit much lower speeds, wind shears are likely the result. As Fletcher said, Jupiter has a complicated but repeatable pattern of winds and temperatures in its equatorial stratosphere, high above the winds in the clouds and hazes measured at these wavelengths. If the strength of this new jet is connected to this oscillating stratospheric pattern, we might expect the jet to vary considerably over the next 2 to 4 years. It'll be really exciting to test this theory in the years to come. In contrast to James Webb's brilliant successes, one of NASA's key projects continues to fall into a deadlock. In recent years, NASA has acknowledged that its large space launch system, rocket, is unaffordable, and has sought to bring its costs down to a more reasonable level. The most recent estimate is that it costs $2.2 billion to build a single SLS rocket, and this does not include add-ons such as ground systems, integration, a payload, and more. Broadly speaking, NASA's cost reduction plan is to transfer responsibility for production of the rocket to a new company co-owned by Boeing and Northrop Grumman, which are key contractors for the rocket. This company, Deep Space Transport, would then build the rockets and sell them to NASA. The space agency has said that this services-based model could reduce the cost of the rocket by as much as 50%. However, in a damning new report, NASA's Inspector General, Paul Martin, says that is not going to happen. Rather, Martin writes, the cost of building the rocket is actually likely to increase. Our analysis shows a single SLS Block 1B will cost at least $2.5 billion to produce, not including systems, engineering, and integration costs, and NASA's aspirational goal to achieve a cost savings of 50% is highly unrealistic. Martin wrote in an audit of the agency's plans, which was published on Thursday. The main problem with the CELS rocket is not its performance. The vehicle's debut during the Artemis I mission in late 2022 was virtually flawless, but rather its extremely high cost. Independent reviews of the vehicle, which Congress mandated that NASA build more than a decade ago, have found that NASA is unlikely to have a sustainable deep space exploration program built around such an expensive, heavy-lift rocket. Digging into Martin's report, it's not difficult to see why. The SLS rocket is powered by 4 main engines derived from the Space Shuttle program. The cost of these 4 engines is $587 million or $146 million per engine. This means that a single engine on NASA's rocket costs roughly the same amount that the space agency paid for an entire mission on the Falcon Heavy rocket, $178 million, for the Europa Clipper spacecraft. Seriously, stop and think about that. As Martin wrote in the new report, given the enormous costs of the Artemis campaign, it is crucial that NASA achieve some significant measure of its affordability goals. Failure to do so will significantly hinder the sustainability of NASA's deep space human exploration efforts. However, as Martin said, NASA's approach to saving money is unlikely to work. Martin bases his conclusion on a number of persuasive factors. But the main reason is that NASA's estimate of a 50% cost reduction appears to be based on magical and wishful thinking. Boeing is the contractor that builds the core stage of the SLS rocket, which includes the propellant tanks and 4 main engines. Martin notes that Boeing only reduced its workforce by 13% as it moved from building the rocket's first core stage to the second one. Then the report dryly adds, Boeing historically has increased costs under their contracts. Nor are savings likely to come from the engines, despite the fact that their per-unit cost is nearly $150 million. Rather, Martin's analysis finds that the cost of future engines is likely to go up. Despite initiatives aimed at cutting costs by gaining manufacturing efficiencies utilizing 3D printing and using less costly materials for RS-25 engines beyond Artemis 7, we instead found cost increases for future engines. Martin also notes that there is no incentive for deep space transport to lower its prices. The agency is not committed to move to fixed price contracting and has allowed Boeing to incorporate limited rights data into the design of the core stage. In other words, no one else can build the SLS rocket, so if the space agency wants to continue to buy them, it must do so from Boeing and Northrop. Finally, Martin cites history. In the mid-1990s, NASA transferred the space shuttle production from agency management to a commercial services contract, citing the goal of saving money. Boeing and Lockheed Martin created a new company, United Space Alliance, to provide shuttle services on a sole source basis to NASA, like what will be done with the SLS rocket. So, did costs go down? Alas, no. As a result of the transfer of shuttle production and operations responsibilities from NASA, managed contracts to a commercial services contract, we estimate space shuttle operations costs increased approximately 38% to $1.45 billion per launch, Martin wrote. As part of his report, Martin makes several recommendations to NASA. Perhaps most strikingly, the Inspector General suggests that NASA consider using commercial heavy lift vehicles as an alternative to the SLS rocket for future Artemis missions. The agency may soon have more affordable commercial options to carry humans to the moon and beyond, the report states. In our judgment, the agency should continue to monitor the commercial development of heavy lift space flight systems and begin discussions of whether it makes financial and strategic sense to consider these options as part of the agency's longer-term plans to support its ambitious space exploration goals. The politics of this are messy, of course. In 2010, Congress directed NASA to build a heavy-lift rocket and crew capsule using existing contracts from the canceled Constellation effort, and this resulted in the SLS rocket and Orion spacecraft. Congress has tended not to care as NASA has racked up tens of billions of dollars in development costs for these vehicles. This may or may not change given the likelihood of budget cuts in the near future. But what now seems clear is that the SLS rocket will never cost less than it does now, and it probably will cost more in the future. Perhaps it is, indeed, time to consider an off-ramp before NASA signs contracts to buy SLS rockets for the next decade or two. As a piece of good news, the warm afterglow of a world's shattering collision between two massive planets has been seen for the first time after astronomers trained their telescopes on a distant sun-like star. The cataclysmic event is believed to have destroyed a pair of ice giant planets that slammed into one another to produce a shower of debris and a hot, spinning object potentially hundreds of times the size of Earth. According to Dr. Matthew Kenworthy, a co-lead author on the study at the Leiden Observatory in the Netherlands, it would be very spectacular. The energy of the collision would turn the remnant into something resembling a star, fainter than the main star in the system, but about 7 times larger in the system, but about 7 times larger in size, visible all through the rest of the stellar system. The discovery came about after an amateur astronomer responded to a social media post from Kenworthy about a star known as ASASSN 21QJ, Kenworthy was looking for shadows cast by giant rings around planets as they crossed the face of their parent star. ASAS SN21QJ, which lies 1,800 light-years from Earth, piqued his interest because in December 2021, it suddenly and inexplicably dimmed. On reading the post, Artu Senio, a volunteer citizen scientist for NASA, checked past observations of the star by NASA's NEOWISE mission, an infrared space telescope. He found that 900 days before the star dimmed, NEOWISE saw a steady and sustained brightening of infrared light from the same location. "I was looking for something completely different," Kenworthy said. The infrared brightening told us something unusual had happened in the neighborhood of this star. And so it took us down this new path. After a detailed analysis of the observations, the astronomers concluded that the blast of infrared radiation came from a hot new object, or synestia, created by the collision of two planets nearly as large as Neptune. Based on the infrared readings, the vast spinning object had a temperature of more than 700 C for about 3 years. It will eventually cool and form a new planet around the star. According to details published in Nature, the star began to dim about 2.5 years after the afterglow began, as a massive cloud of fine impact debris drifted across the face of the star. As Simon Locke, another co-lead author at the University of Bristol, said, "It's the first time we've seen the afterglow from such an event. We've seen debris and disks before, but we have never seen the afterglow of the planetary body that's produced." Astronomers are now keen to follow up the observations to confirm what they suspect has unfolded. If the dust cloud continues to orbit the star, then in about 5 to 10 years, the cloud will have moved to one side of the star, and astronomers should see the star's light reflected from the dust with the largest ground-based telescopes. It may also be possible for the James Webb Space Telescope to detect infrared radiation from the dust and the new planet created in the collision. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.